Hello, this is the linear modelling unit, or linear modelling lesson. So linear modelling, it's really just a recap of something we did in coordinate geometry last year. So linear modelling, remembering a linear model is in the form of y equals mx plus b. You might think of it as y equals mx plus c. You might think of it as y equals ax plus b. That's all okay. So in my case, y equals mx plus b. What does the m stand for? You might remember it stands for the gradient, which is a rise over the run. Rise over the run. Or you might think of it as the gradient formula. Rise over the run, y2 minus y1 over x2 minus x1. If you're looking at two coordinates, x1, y1, x2, y2. What does the b stand for? And I think that's right, the b stands for the y-intercept. Probably remember this though. So the y-intercept is a b, m is a gradient, which is rise over run, or y2 minus y1 over x2 minus x1. So you're asked in the space below, draw a sketch of this type of function and write out its general equation. So let's see page 3 and 4 if you've got it. So page 3 and 4 of this book has kind of like some examples of different functions, and linear function happens to be there. So notice you've got a lot of space to do this in. And then what are some features of this type of function? So to start with, we draw a coordinate plane. Please use a ruler to do it. Don't do what I'm going to do. Don't do as I do. This looks pretty nice. Here's my x-axis, here's my y-axis. Better than normal. Here's my x and here's my y. Classic thing, people forget to label their axes. Please always label your axes. Don't give us any reasons to take off marks, because we will, just to be mean. Now, linear function, like you could draw a straight line, and it could be, if it had a positive gradient and a positive y-intercept, it could be something like this. There, that's totally fine. So you could do that one. Alternatively, you could do one with a negative gradient and a positive y-intercept, which would look like this. Alternatively, you could do one with a positive gradient and a negative y-intercept, which would look like this. You could also do one instead with a negative gradient and a negative y-intercept, which would look like that. If you did something as simple as y equals x, it would probably look something like this, maybe a bit flatter. If you did something as plain as y equals negative x, like basically it's got a y-intercept of 0, it might look like this. Okay, so I'm going to do one like I did at the beginning. So our general equation is y equals mx plus c or mx plus b, do whatever one makes sense to you. So therefore our c would be our point here, because it's the y-intercept. So the y-intercept, and our gradient is n. No surprises there. Just pointing out what we said below. So m is the gradient, which equals the rise over the run. Or you might think of it as y2 minus y1 over x2 minus x1. In this example, the gradient is positive. So in this example, the gradient is positive, and you just write whatever it is for your one. So it's positive for me because going from left to right, it's going upwards. If from going from left to right, it was going downwards, I wrote position instead, positive. So it's going downwards like that instead, it would be negative. My y-intercept happens to be positive as well. Write out its general equation. We've done that, y equals mx plus c, and all that kind of stuff. Down below it says, what are some features of this type of function? So it's a straight diagonal line. Some people might have asked, what if it was a positive or a horizontal line? In that case, it's not a linear function anymore, it's a constant function. Like if it's a horizontal line or if it's a vertical line. It's no longer linear, it's because it's got no gradient. So it's either got a gradient of 0 or an undefined gradient. Gradient of 0 would be this one, wouldn't it? because the rise is infinite and the run is 0. Nope, the gradient of 0 would be this one, because the rise is 0 over an infinite run, and so that equals 0, whereas the gradient of a vertical constant function would be undefined, because it's an infinite rise over a run of 0, and you can't divide by 0 in maths. So vertical gradients are undefined. So if it's a linear function, it's got a gradient that's non-zero, or it's actually even defined to begin with. So it's a straight diagonal line. So a straight diagonal line, that's one feature. So important, it has to be diagonal, not vertical or horizontal. It has a y-intercept. Linear lines have y-intercepts and they have x-intercepts. So there's a y-intercept and an x-intercept. Here's our x-intercept right there. So it has a y-intercept of c. We'll use b if you use c. So it has an x-intercept. And where the x-intercept lies is where y happens to equal 0. At y equals 0. The y-intercept is also at x equals 0, of course. Trying to think of anything else. The gradient could be positive or negative. Could be positive. So going up like this. Or negative. In which case it would be going down from left to right. Can you think of any other features? Trying to think of anything right now. Can't think of anything special that comes to mind. It's not curvy. Oh, domain and range, let's put that. So unless it kind of states otherwise, assume as a domain of XER and a range of YER. It is a function, so it is a function as proven by a vertical line test. Vertical line test. Trying to think of anything else. I can't think of anything too groovy right now. So let's move on from that. Linear functions in general. Let's try an example where it would be more like an investigation situation, and we'd be asked to model bamboo growth. So actually using linear models to model bamboo growth. So bamboo, it's the fastest growing plant in the world. So you might notice that bamboo is becoming popular in terms of making fabrics. Like you might have seen people have bamboo t-shirts. It's nice and soft and light, and it doesn't use, because it doesn't use much water or it doesn't use much land. That's why it's eco-friendly. So it's the fastest growing plant in the world, with some species growing up to 1 meter per day. Zhuanyu planted a 30 centimeter high bamboo plant in her garden bed. She found that with consistent weather, it grew 10 centimeters each day. So that's its initial height, and that's the rate at which it's growing. So what would be its y-intercept? So y-intercept would be at time 0, when she first planted it in the ground. How high is it? So the height would be 30, so the y-intercept would be 30 centimeters. What's its gradient? So as you go across by 1 day, it goes up by 10 centimeters each day on the graph. So it's got a gradient of 10 and y-intercept of 30. Probably given away too much already. So what to do? Copy and complete this table of values, which gives the height of the bamboo after t days. So that's like x and y, but instead we're calling it t and h. So we've got 0, 1, 2, 3, 4, 5, 6. So obviously at 0 days, when she first planted it in the ground, that was the initial height. So this one here is the initial height, not the initial height. This is the initial height at time of first planting it. That's kind of a weird way to word that. Feel free to word it in a much better way. So that's the initial height, just in case they ask you that. So after 1 day, of course, it's gone up by 10 centimeters, because according to our question, it grew 10 centimeters each day. So when she first planted it, it was 30 centimeters high. Then after 1 day, 40. How high would it be after 2 days? And it's a linear function, so we're going up by the same amount each time. Plus 10, and so on. What would it be? That's right, it would be 50 after 3 days. So just double check in a table that we're not jumping up ahead a few days, but in this case we're not, we're just going up 1, 2, 3, 4, 5, 6 days. So 50, what would be the next one? That's right, 10 more, 60, add 10, 70, 50, add 10, 80, 60, add 10, 90 centimeters. Woo! Okay, so plot the points on a set of axes, and I've kind of tried to help you by putting that in there, or the book that I stole this from did. Plot the points on a set of axes and connect them with straight line segments. Basically draw a line of best fit through it. So plot the first point. First point is 0, 30. Oh, it doesn't have any kind of like things on it. So let's put some things on it. What are they called again? Scales. So 1, 2, 3, 4, 5, 6, 7. We only need to go up to 6. Our thingamajiggy, our y-axis, or the height axis, has to go up to 90. Or does it need to go, let's see, how long will it take for the bamboo to be a metre high? Maybe you want to go up higher. So where we go? 40, 50, 60, 70, 80, 90, 100. Nice. So let's go by 10s. 20, 30, 40, 50, 60, 70, 80, 90, 100. Make sure that the scales always go up in regular intervals. So notice it's already labelled. It says T days on the horizontal axis, and it says height in centimetres on the y-axis. If it didn't have that in there, we would have to put that in there. We have to label our axes. It's really important in these modelling thingamajiggies. Now we can go plotting our wonderful data, if you might call it. 0 and 30. Here's a little point. You can use a little X if you prefer, whatever you've been taught to do. I use a little dot. 1 and 40, 2, 50, 3, 60, 4, and so on. You do it. Feel free to just check it with mine. Some people by accident plot these things wrong. Remember, we go across by the X and go up by the Y. So, no, we don't go any higher. Okay, it stops at 690, so we should stop it there. So we've plotted the points. Yay. But have I connected them with straight line segments? No, I haven't. So I need to connect them now with straight line segments. So let's do that. Alrighty. Let's make a line, and I'm going to pick a nice colour. Let's pick this nice blue. No, blue, not exciting. Let's use yellow. Look at that, connecting with straight line segments. Sometimes you might want to go a bit further. It depends. Like if it says plot it only from 0 to 6, like over the domain 0 to 6, you've got to stop right there. If not, you could probably keep going. For now, I'll just stop right there because I don't know. At this point, I could always go back and extend it if I need it later on. But for now, just to be on the safe side, I'm only going to plot it over the domain that we've been given, which is sort of to some extent 0 to 6 and up to 90 as well. So that's a nice straight line. So now we've answered question 2. We weren't asked to put a model or anything with it yet, so that's why I'm not putting an equation with it. Explain, this is question 3, explain why it is reasonable to connect the points with straight line segments. Yeah, this is pretty broad. What's one thing you could say? So as opposed to using a curve, like why would you use a straight line here instead of using a curve? So you could say the height forms a linear pattern. You could say there is a constant gradient. I don't know why the board's a bit wonky today. Constant gradient, which indicates a linear function or linearity. It might be appropriate. So there's a constant gradient, it's going up by a constant amount. If you go across by 1, it goes up by the same amount each time. So which indicates linearity. If it wasn't constant like that, it might not be linear, it might be quadratic or cubic or something else. That'll do for now. Question 4. Discuss whether it is reasonable to continue the line for t is less than 0. So less than 0, for times less than 0, and for times greater than 6. hence state the domain of the function. So this is kind of interesting. It's a bit kind of like, would in the real world, would we go to times less than 0? Probably not, because we don't go backwards in times. Not for t is less than 0, as we, in this universe, we don't go backwards in time. In our kind of universe, we go forwards in time only. We can't control time at this point in our evolution. So not for times less than 0, we don't go backwards in time. What about for times greater than 6? So it's kind of interesting. Times greater than 6. At this point, we don't know what happens. Like maybe after 6 days, and as we said, like, is there a limit to how high bamboo grows? Maybe it doesn't grow higher than kind of like 90 centimeters, or maybe there's a certain amount of nutrients in the soil. We don't know what's going to happen after 6 days. Maybe it'll, don't draw this, but maybe it'll flatten out like that, or maybe it'll curve up. We don't know. Is it going to keep following that trend? So at this point, you probably could argue that it could, because it seems to be going pretty constantly. But there might be a certain point where it does slow down its growth, and maybe it sort of hits a sort of peak at some point. I don't know. Or as it just gets older, it starts to wither a bit at the top, so it doesn't become as tall. So you could say, let's go into the other part down here. So for times greater than 6 days, it may be possible to continue. Let's say to continue, let's say, what did they word it? To continue the line. But we don't know for sure if the growth will tend to be linear. If the growth pattern will continue to be linear. E.g., it may slow down due to various factors. And so on. E.g., competition for space, if you happen to have a lot of plants. E.g., competition for nutrients in the soil. Nutrients in the soil due to other plants being there, using the nutrients in the soil. Withering, etc. So it could instead go kind of straight like this, and then maybe it could flatten off after time is 6. We don't know after 6 days what happens. So hence state the domain of the function. Therefore, we could state the domain as being, so it does include 0 days, so 0, 2, and what are we using instead of x? Because domain is x, but instead of x we're using t. 0 to t, and up to and including 6 days for now. So we could state the domain as being 0 to 6, and including 0 and 6, because we do actually have points plotted at those points. Did they ask for the range? No. In question 4 they just wanted the domain. That's question 4 continued. Question 5. Find the h-intercept and gradient of the line. You can probably see that just by looking at the graph. So the h-intercept happens to equal this little point right here. It's 30. And it's, what's the units? It's centimeters. And the gradient of the line is rise over run. Rise over run. Or you could do y2 minus y1 over x2 minus x1 using 2 coordinates. We can see it goes over 10 by 1, 10. The gradient has no units because centimeters over centimeters cancels out. So it's just got a gradient of 10. So you might want to circle them so when you look back you realise that they're your answers. 6. Find an equation for the function h of t. So notice they're using the height with respect to time. So it's an example of function notation. So the gradient is 10. And then it's t for time instead of x. Plus 30. So y equals mx plus c. We're basically using y equals mx plus c as our method. So y equals mx plus c is our method for that. H of t, so we, instead of y, we say h of t, the height with respect to time, equals a gradient of 10 times the x, which is t instead, because it's time, plus 30. So that was our equation in the yellow box. Use your equation to find the value of h of 10. So remember back to function notation, h of 10 just means sub in 10, where you see x, or time in this case. So instead it'll be 10, and the time means 10 days. 10 plus 30, which is 130 cm. So explain what this value represents. It's the height after 10 days. It's right there. It's the height after 10 days. Feel free to use the space down the bottom of the page if you are having trouble kind of like fitting it in here. It's the height after 10 days. Now, how long will it take for the bamboo to be 1 meter high? So 1 meter, remember, is the same as 100 centimeters. So they want to know how long, what would be the time? So I'm going to answer question 8 down here. So I can give myself a bit of space. So our function, remember, is, function is the height with respect to time equals 10t plus 30. So if we said 10t plus 30, I want to know for it to be 100 meters high, 100 centimeters high, which is 1 meter. What's the time going to be? So now we're going to solve. So what's 100 minus 30? 100 minus 30 is 70. So 70 equals 10t. Hang on, if I read this right. How long will it take for the bamboo to be 1 meter high? Oh yeah, okay, cool. And then 70 divided by 10 is 7. So it would take 7 days. You could use your graph as well. I would use your equation. Sometimes a question in an exam might say use your graph, or it might say use your equation. So make sure to use what they said to use, and then feel free to use the other method to check your answer. So remember, the methods could be using a graph. If you extended this graph to 7 days, you'd get 100 centimeters tall. The plant would be. How long will it take for the bamboo to be 1 meter high? Yep. Okay, so that's done. Thank you very much for your patience, and I hope you enjoyed that.